All right, Newton's second law. Here's there's a force. There's a little guy here. I apply some force to him. Boom! He goes flying off. He accelerates. I apply the same force to this big guy. He goes. Does he accelerate as fast as the skinny guy did? No. So what we see is the acceleration is bigger when the mass is smaller, and we say that that is an inverse relationship. As m gets bigger, a gets smaller. Here's a skinny person again. Yes. Little tiny baby gives him a shove. He will accelerate a certain amount. A bigger person gives him a bigger shove. He will hopefully realize accelerate much faster. So here we say that the acceleration here would be proportional to, this is a proportional sign, the force. And so what we see is that the acceleration seems to be proportional to F over m. And we define the units such that we don't have to make any changes. We say that A equals F over m, and so therefore F equals ma. Very general formula, we'll be using it frequently. Force acting on an object is equal to its mass times its acceleration. Let's put it into action here. I see a force of 150 newtons is going to accelerate a block where the mass is 25 kilograms. What is the acceleration of the block? So what we have here is a straight plug-in type question. I see the force of 150 newtons. I see the mass is 25 kilograms, and I'm looking for A. Wait a second. One mark. Check. The force, F equals, formula. Check. One mark. I plug in, I'll rearrange first. A is F over m, which is 150 over 25, which is 6 meters per second squared. Third line, check, straight. There's the formula in action. Now we'll do a bit more complicated question here. Here's a little car that's got a string attached to it. The string goes over a pulley. It's attached to a mass. When the mass is allowed to fall, everything's going to move here. And we're interested in how fast will they accelerate, and what is the tension in the string. Yes? What is this tension in the string? And for both, since there's a rope or a string attached to them, they will have the same A, and the tension is the same throughout this rope. There's no like soft or gaps or parts laying down. The tension is tight all the way through, so T and A are constant through the whole problem. Now in any of these questions you do, the first thing you should do is draw a free body diagram. In this case, we should draw 2 free body diagrams. Right there. What forces are acting on this guy? Well, gravity pulls him down, and the normal force pushes him up, and those are equal and opposite because it's not flying off the table and it's not going into the table. We'll say there's no friction on this, so we'll say that the only thing pulling it this way is the tension in that rope. Now, this block, gravity is pulling it down, tension is pulling it back up. Next thing we're going to do in all these questions is we're now going to write an equation for net force. F net acting on that guy, and F net acting on that guy. Which one of these two forces is bigger? Well, hopefully we realize this thing's going down, so gravity's got to be bigger than tension, so I'm going to put Fg minus T. And over here, since these two are canceling each other out, in the y, I'm only interested in the x, and it looks like the only guy there is t. This is a key point so far. So step 1, free body diagram. Step 2, equation for net force. Step 3, instead of having F net, we're going to use our brand new, super new, fancy dancy formula, F equals ma. There it is right there. Boom. So instead of writing this, I'm going to write m1a equals t. And over here, I'm going to write m2a equals, force of gravity is mg, 2 minus t. What did I say the masses were? 3 and 5. So this is 3a equals t. And over here I get 3a equals 3 times 9.8 minus t. And now I've got to substitute. I've got an equation here with a's and t's. I've got an equation here with a and t. I'm going to substitute. I'm going to do that. I'm going to bring these guys together. Now there's three ways to solve two equations, two unknowns. I can substitute, I can compare, or I can eliminate. Eliminate would also work nicely here. But I am going to just substitute, so I'm going to put t, 3a, I'm going to put it right there. Look at that. This 3a, that's what t is, I'm going to put it right there. And then I'll have an equation with only a's in it. So I'm going to get 3a, slow down, 5, not 3, grrr, made a boo-boo. I know everybody watching the video is like, what's Prophet doing? He's an idiot. I gotta change that. Let's put a 5 here. Put the wrong math, so I use the same math in both places. Excellent. I know you were thinking it. This guy's gotta go 2, that's a 5. So here's 5a equals 5 times 9.8 minus, not t, 3a. I'm going to bring this guy over to this side, and it's going to become a plus, so I'm going to get 8a equals 5 times 9.8, and then a, to get a by itself, I'm multiplying here, I'm going to bring it over and divide. 5 times 9.8 divided by 8. Do that's like 50 over 8 or thereabouts, and then that would be 6.2 meters per second squared. So this thing's going to start accelerating down at about 6.2 meters per second squared. Am I done? No! I found A. I haven't found T. Still need T. Well, I know T equals, since T equals 3a from right up here, I'm just going to plug my A in here. I'm going to get 3 times 6.2, 18.6 newtons. Now I have completed the question. I have A and I have T. So let's review what are the steps for all questions like this. Free body diagram for all the objects involved, equation for net force, plug in MA and MA for net force. Probably going to get a system or scenario where I have two equations, two unknowns. Sometimes I get 3 equations and 3 unknowns. It's not the end of the world. I solved them simultaneously. Here I solved by substitution. I got an answer, and then I plugged back in to get my the other variable that was being asked of me in the question. Newton's second law, F equals ma.